Hi everyone, welcome back to another video. Now that we've learned how to set up your account and save files and that sort of thing, let's run you through your very first lab in every circuit. So this lab is called the Bipolar Junction Transistor Lab, and we'll be using the lab manual created by Professor HR while we're going through this lab. So keep that handy while you have it. The circuits that I design in this lab don't necessarily follow the particular criteria that professor has laid out for you. So the beta value of the transistor, the IC value, and the BCE value. So make sure you're actually using your particular values for resistors and the beta value for the transistor while you're doing this experiment. But I'll be showing you with a beta value of 100 and just some random resistor values just to get the concepts through. So last but not least, let's build our first circuit. So the first circuit is called the fixed bias circuit. So we're going to need two resistors, and we're also going to need a transistor. So we'll just drag and drop those onto our breadboard. And we'll also need a positive 15 volt source. And you can see the source is flipped right now from how we need it, because we need the positive terminal up here. So let's go ahead and click F, or you can use the shortcuts down here on the GUI version. And then we can connect all the nodes. So go ahead and connect those up. All right, now last but not least, let's place a ground node on the back of your voltage source. For any simulation to run in this tool, you need to make sure all your circuits are grounded out properly. So let's go ahead and flip that again. And we'll place that on the back of right now our 1 volt source, but we're going to switch that right now using the adjust tab. So hit A or adjust. And you should be able to switch that to 15 volts. And you can use these little fine tuners here to get it a little closer to where you want it. For an RB value, let's just use something around 8K. And for this value, let's use something around 600K. All right. So let's go to 1 mega ohm. All right. So now that the circuit is all hooked up correctly, we can go ahead and look at what it's asking us to do. So we need to confirm the transistor is in active mode. So for an active mode, the voltage at this node, the VC node, should be higher than the VB node, should be also higher than the VE node for an NPN transistor. And I've added now a wire that I have to delete. And you can delete a wire very easily by hitting the delete key on your keyboard. Just highlighting the wire and then hitting the delete key. That'll work for you. So once the circuit is hooked up correctly and we feel like we're good to go, let's go ahead. Actually, one more thing. Let's just show you how you're going to change the beta value of your transistor. So in here, your transistor, you're going to go to the adjust menu as well, and you're going to adjust the forward beta. So in your case, for your lab, it would be 220. I'm just showing you here for just teaching purposes that the beta is 100 that I've used. All right, now let's go ahead and run this circuit. So we can see there's 1.43 milliamps in the collector branch, and there's 3.58 volts on the top of the collector. There's 7.29 volts on the base, and there's 0 volts on the emitter as expected. So we can see that this transistor is clearly in active mode. The next step in this lab is to reduce the value of RB by 20%. So we'll go ahead and we'll look at the value of RB that we've chosen, which is 1 mega ohm, and we'll reduce that by 20%. So that'll put us to 800 kilo ohms. And once we've done that, we can go ahead and rerun the circuit. Now we can see that the VE value is 0 volts, the VB value is 735 millivolts, as well as the VC value, which is 735 millivolts. So now we can see this transistor is clearly not in active mode, as the VC value and the VB value are exactly the same. So we can go ahead and answer the third question, which is commenting on the sensitivity of this circuit to changes in RB. So make sure to include that in your lab report and go ahead and save this for your TA to view. .1.1. And as your description, make sure you enter your username and make sure you're saving them as private, and you're going to go ahead and save that file. So now we see that file is saved and the TA can go back and view it later on. So now the next circuit we're going to make is the voltage divider circuit, which is the self-bias circuit. So go ahead and pause the transient analysis and we'll rewind. So get everything off of our screen, and we can delete this wire. We can delete this wire and keep all other wires as they are. We'll just move down that ground node because we need to put another resistor in there. And we're going to add 2 more resistors. So we're going to add an RE value and an R2 value. We also need 1 more ground node for the bottom of R2. Okay, now we can go ahead and tinker these values. So what I've chosen is obviously not what you guys are going to be doing in your lab, but I have chosen values that will give me a current of 1 milliamp on IC. So I've chosen 8.8K, RC should be 7K. Okay, and 2K. So now I can go and run transient analysis again, and we see that this transistor is clearly in active mode. My VC value is higher than my VB value, which is also higher than my VE value, which means that this NPN transistor is forward bias in this junction. It's reverse bias in this junction because we have higher than a 0.7 volt drop. And we have right around 1 milliamp coming into our collector. So now it wants us to reduce both the resistor values of R1 and R2 by 20%. And note the values of IC, VCE, and VBE. And note the mode of operation for the transistor. So let's go ahead and reduce these by 20%. So 20% of around 10K, let's say it is 6K. .400 ohms, so this should be around 1.6. And now we see that the transistor is still in active mode. So we can also now comment on the sensitivity of this circuit to changes in R1 and R2, and we can compare these results of the experiment from results 4.1.1. So we can comment on the sensitivity of this circuit in changes in R1 and R2 compared to the sensitivity of the previous circuit's changes to RB. And now we can go ahead and save this circuit as 2507 Lab 4. And we're going to call this one 4.1.2. And we can call it self-bias. Make sure to save it with your username in the description and go ahead and click save. So now we have two files here. We have our circuit from 4.1.1 and we have our circuit from 4.1.2 that the TA should be able to go and check in on. They're both private files, so only you and the TA should be able to access them. So now, make sure you've made your comments on the sensitivity changes of the fixed bias circuit compared to the self-bias circuit. And make sure you comment on the mode of operation when you reduce the RB and the R1 and R2 values by 20% in both situations. Make sure you've done that and included that in your lab report. And now we can go ahead and make the final circuit, which is called the BJT amplifier. This is probably one of the more tricky circuits that you're going to make in this course. So let's go ahead and get started. I just started with a copy of my last one. We can go ahead right away and save it as 4.2 BJT amplifier. You don't have to change anything in the description. 2507 is fine and lab 4 is fine. Go ahead and click on save. That'll make a new file for us. So what we need in this circuit, as you can see, is two capacitors to begin with, another resistor, and an AC sinusoidal wave. So let's go ahead and add those to our breadboard. So we're going to add a 1 kilohertz sine wave. We're also going to add another resistor that we want to flip. We're going to add a capacitor that we also want to flip. There we go. And once we've done that, we'll just add our last capacitor on the output. And we'll go ahead and connect everything up. So once everything is connected up, we can go ahead and add a ground node to the bottom of our 1 kilohertz source to make sure everything's grounded. This node, however, doesn't need a ground. As you can see from the diagram, it's not actually connected to anything. We're just measuring the open circuit voltage here. So we don't actually have to connect that to anything. We'll go ahead and change the values of these capacitors to 10 microfarad for each of them. In a regular lab setting, these capacitors have polarity. So the positive side would need to go on the higher potential voltage, which is actually right here. And the negative side would actually go on the lower potential, which is actually out here. I know it's not very intuitive to see right now, but you'd be able to see that in a lab setting. Okay, so let's go ahead and switch this value to 10K as prescribed. And we'll switch this to a 2 volt peak to peak. Now we can go ahead and we can run the transient. When we're running the transient, what we want to see is we want to see the output versus the input. So let's go ahead and click on those particular waveforms that we want to view on our screen. Those will help us the most. So let's click on that, and we're going to click on View Waveform. which is the same as clicking the W button on your keyboard. You could do either or. And we also want to look at our input, which is this wave right here. So whatever wave you're currently selected, it will give you the parameters of that wave right below the scope. So let's say I want to go back here and see what my parameters of this wave are. We can see that its minimum is at 6.97 and its maximum is at 8.88. There is roughly around 2 volts between those two. So we're roughly getting a 1-to-1 input on our gain, which is exactly what we're looking for in this lab. But the only difference is, why is this one up here and that one is down there? It's something to do with the fact that these channels don't allow you to AC or DC couple. Because these scope channels don't AC or DC couple, you're going to have to go in here and figure out why exactly the green one is centered around 0 volts, whereas the purple wave, which is my output wave, is centered around what looks like to be 8 volts from this graph. And you're just going to have to explain what the difference between AC and DC coupling does and why the one wave is centered around 8 volts and the one wave is centered around 0 volts. So once you've done that, you can look to calculate the input current and the input resistance of the circuit. So this is much easier than it would be in the lab. Let's go ahead and pause our simulation for now, and we'll rewind. So now that the simulation is stopped, we can go ahead and delete this particular branch between the capacitor and the resistor, because we can add an ammeter between those. An ammeter goes in series, and an ammeter will directly measure the current in a branch. So the ammeter is going to connect that side of the 10 microfarad capacitor and the right side of the 10 kilo ohm resistor. And then he should be able to, as long as we view his waveform, we should be able to see the peak-to-peak voltage, the peak-to-peak current through that branch. So let's go ahead and run the transient analysis again. And we can see, since we've chosen the current waveform right now, it's showing up in a current scale. And we can get the peak-to-peak values. So we can have the min and the max, which gives us the peak-to-peak value for the current. From there, we use the peak-to-peak value for the voltage in that we have, which we know is 2 volts peak-to-peak. And we divide that by the current that we have. So we can calculate the input resistance for this circuit. Last but not least, we're going to look at the large signal distortion. So we're going to increase the amplitude of the AC wave that we're inputting until we see the output, which is the purple wave, starting to distort. So let's go ahead and we'll hide the waveforms for the current and for the input. So we're just viewing the output waveform now. And this is a good place to start. So we'll increase the input until we see the bottoms of the waveform start to clip. Doesn't look like it quite yet. And it looks like there it's kind of starting. There it's a lot more pronounced. You can definitely see that there. So I would note down that voltage where your bottoms start to clip, or your peaks in your case. And next we will sketch that. So don't have to sketch it, just include a screenshot for your report for the TAs. And now we're also going to increase the large signal until we see both the tops and bottoms start to clip. So at 30 volts, we're well over that. And this is a good waveform to draw of what exactly is happening when you're clipping on both the positive and the negative half cycle. So without further ado, I believe that is everything that you've needed to complete for lab number 4, the BJT lab, for ELEC 2507. If there is any problems or any concerns, please let me know. Don't hesitate. And I hope to see you guys again in the MOSFET video where we can tackle that lab. Bye-bye.